ఐఐటి అతని పేరు ఏం పేరు వెళ్దాం సార్. ఐఐటి అతను ఏం పేరు అతని పేరు తిరుపతి రవిశంకర్.
ಹೇಳಿ ಹೇಳಿ ಪೇಮೆಂಟ್ ಚೆಕ್ ಕೊಟ್ಬಿಡ್ತೀನಿ.
లేదా
Sir, shall we start, sir?
Yes, yes.
Around 38 participants joined. They will join. Actually, in the morning session, there are some little bit late.
Oh, I see. I see. No problem. Yeah, yeah.
Maybe they are in the lunch break.
Yes, yes.
So we start. In the meanwhile, they will join, sir.
No problem. No problem. So, should I begin?
Sir, I will introduce, sir. After that,
Okay. Yeah, please.
so good afternoon to all of you. So today we have the afternoon session. We have Dr. Shantanu De, sir. So sir is working as associate professor in the mechanical engineering, IIT Kanpur, Uttar Pradesh, India. So before handovering the session to the sir, I will introduce. I will read about the brief bio sketch about the Shantanu sir. So Shantanu sir did the PhD in the aerospace engineering from Indian Institute of Science, Bangalore, under the specialization of propulsion and combustion. So sir did the Master of Technology in the mechanical engineering from IIT Kanpur under the specialization of fluid and thermal science. So graduated from mechanical engineering from Jalpaiguri Government Engineering College, North Bengal University, West Bengal. So sir is having the professional experience as associate professor at IIT Kanpur from December 2019 to till date, and assistant professor the same in the at IIT Kanpur as assistant professor, and a research associate at Institute for Combustion Technology, University of Stuttgart, Germany. Research associate from 2011 August to July 2013, engineering mechanics, Michigan Technological University, USA, and also scientist at Liquid Propulsion System Center, Indian Space Research Organization, Valyamala, Trivandrum, Kerala. And sir is having awards and honors. Early Career Research Award from DST sir, and also sir is the recipient of the National Doctoral Fellowship from All India Council of Technical Education in the year January 2006 to December 2008, and the Best Commented Paper Award for the journal article Simulation of Laminar Flow in a Three-Dimensional Lead-Driven Cavity by Lattice Boltzmann Method from Emerald. So sir is having teaching experience at IIT Kanpur. Sir taught many subjects: energy systems, combustion and environment, introduction to the turbulence, modeling of turbulent combustion, energy systems. At ITV Stuttgart, advanced combustion fundamentals, physics and chemistry of combustion taught. And sir is a vast research experience in turbulent spray combustion. So large AD simulation of reacting spray jets are carried out using advanced models for turbulent combustion, flamelet progress variable approach, conditional moment closure method, and also turbulent reacting spray flames are modeled using Reynolds averaged Navier-Stokes based combustion model. The sir is also having research projects. There are some of the projects are ongoing and one completed projects, and organized many courses for the faculty and the students. So and also sir is guiding many PhD scholars, MS scholars, and MS students. And sir is having 18 publications in the reputed journals and 14 conferences, conference abstracts, 7 edited books. 3 books are edited by Shantanu sir, and book chapters 9 published. So this is the only few details about the Shantanu sir. So with this, I would like to request Shantanu sir, please proceed.
Thank you, Professor. Thank you for your nice introduction. And I hope that I am audible to all participants. And it is very nice to see all of you in this course. And I hope that it will meet your expectations, and you will be able to learn something from various speakers that Professor has, contacted, and they have agreed to deliver talk on different aspects of energy, right? So today I am going to give you a lecture on carbon capture, storage, and utilization, right? So this is a topic. If you can, whatever you heard from Professor, that this is not my area actually, but I thought that this is a very important area, and whatever little thing I could learn, maybe I will share it with all of you. And I have not learned many things, but I learned a few basic things, and I am willing to work in that direction, because that is the need for the hour. Okay. So as a combustion researcher, we should also explore the way to mitigate the bad effect of combustion on basically in our environment. Okay, so that is the motivation, and I just now started some work on this direction. And if you see my profile, I have not published any journal article on this. There are some ongoing works which I can discuss towards the end of this lecture. Okay, so just to begin, I will begin with my brief background and the research interest. Although Professor has already mentioned that, and some of you can visit my website at IIT Kanpur and get more ideas. Basically, I will tell that so far I worked on the modeling of turbulent combustion, and I utilized various models like RANS and the large eddy simulation for the turbulent combustion modeling. And also we have developed different models for turbulent combustion, like the flamelet model, conditional moment closure method, multiple mapping conditioning, and the PDF, transported PDF approach. Okay. So these are, if you go from the flamelet to the PDF, these are on the increasing order of complexity. Of course, that is not the topic of this talk, but if any one of you are interested, you can also approach me, and we can collaborate, or we can work together. So in past I applied this RANS based MMC approach, and then the LES on different gaseous and then the spray flames, and some of the burners like the pilot stabilized burners, lifted flames, etc. are investigated. So also I worked on a very interesting project funded by ISRO. It is on the development of an LES based model for the scramjet combustion, the supersonic combustion of gaseous and liquid fuels. So that is also quite a learning experience for all for me. And here basically the stabilization of the flame when the underlying flow is very much supersonic is very difficult. Okay, and we try to predict such complex turbulence chemistry interactions in the supersonic flows. I also worked on pulverized coal combustion. I guided one master student, and currently I'm working on gas turbine combustion, both experimentally and numerically, right? So we also worked on the primary atomization like sigma Y model. So on the experimental side, we have recently set up a laboratory where we can do the visualization, optical visualization of a complex these flames, right? So basically that will give us a lot of information about the underlying phenomena, basically the turbulence flame interaction. Okay, so this can be done using high speed lasers. Okay, so this is called the planar laser induced fluorescence technique, which is currently being installed at our lab. And we are also trying to purchase a high speed PIV setup, and basically we can integrate these two together, and we can look into simultaneously the velocity field and the combustion field. Okay, So that will be, I think, one of its kind of facility at IIT Kanpur, and it will be probably the first one in India which will have a high-speed PIV PLIF combination, and that can be useful for investing into the flames in gas turbines or any other burners. Okay. We are also working on development of a dual fluidized bed gasifier for Indian coal, which is having a lot of high ash content. Okay, so that gasifier we have already commissioned in the lab, and currently it is under experimentation. We have also designed a micro gas turbine, and it is being jointly developed by an industry from Bangalore, and these two work are basically going to be concluded very soon. Okay. So some of the results from my PhD students, I mean, you can just see, I will not go into the details. We have simulated some of the burners, like the lifted jet diffusion flames, etc. And then we compared our results with the experimental models, and we got very good agreement. So these are the new models which we developed, and we have investigated such flames. So this one is basically the experimental picture, and whatever we have plotted is basically our results, and then the symbols are experiments. And we can see that the variation of the lift off height when the conditions are different, and we see a very good trend predicted by our model. So I'm not, this is another example of a, the experimental and the numerical validations part. Okay. So I will not go into much details. So if you are interested, we can discuss it towards the end, or maybe you can contact me by email, and we'll be happy to share some of the information. So these are some of the results. Now, this is the large eddy simulation. Some of you may be working on this, or you are planning to work on this. So we can basically predict the very complex flame. You can see that the flame is changing instantaneously. So this is the instantaneous temperature, and the flame is basically a lifted flame which is stabilized away from the burner. Here basically you have a liquid, you have a jet with liquid particles. So these are basically your liquid particles which are coming along with the flow, and then it will they will evaporate and then participate in combustion. And this is your OH contour, and you can again see that much of the combustion activity is happening around this location, and yeah, so and so on. Okay, so the next one is basically the time averaged field. So whatever I have shown the video, that one. So this is the DLR scramjet combustor, like a supersonic combustion in scramjet engine. We have done some validations again here for the DLR scramjet combustor with our own models, and we got a very good experiment. On the left side is the DLR combustor, and on the right hand side we have another combustor where it is the liquid fuel is used. In the DLR combustor, it is hydrogen is used as a fuel, and here we are using kerosene as a fuel. And in the both cases, I think we've done a validation work. So this is the coal gasifier, the schematics of the coal gasifier that we have developed. So here we have a gasifier, and then here basically coal is being fed, and the bed is fluidized by fluidizing media, which is basically steam or a mixture of steam and air. And on the left hand side we have a riser where this is the combustor. So why it is called dual fluidized bed? Because one of the these two beds are interconnected, and the bed materials like the sand and the coal that we are feeding, that will come from this loop seal, and it will enter the riser. In the riser we burn the fuel, basically the coal, and it generates a high temperature gas that will heat up the bed materials, and these bed materials will be segregated by the cyclone, and then it will come to the pot seal, and then it will return to the bubbling bed. So basically the bed material goes a path like this, and it carries the heat from the riser or the combustor to the gasifier, because in the gasifier you are providing steam, and you are basically doing a gasification reactions which are endothermic in nature. So therefore you need to circulate the heat generated by burning one part of the fuel, and through the bed materials it is done. Okay, so that is the concept, and this gasifier is suitable for the coal that we have in India, which is having a large ash content as high as 45% in those coal samples, and it is having a fixed carbon content which is about 40%, and it is having very less volatile matter. So such type of coals can be gasified in this, and the gasification product will leave the gasifier and it will come to the cyclone, and then this gasification product is basically the syngas, which is a mixture of carbon monoxide and hydrogen, and they can be taken for downstream applications, either for the power generations in a gas turbine, or you can use this syngas for production of valuable chemicals or the fuels or for fuels. Okay, for example, you can synthesize methanol from this syngas. Okay, so we'll discuss some of these concept throughout this. I mean, in the later part of this talk. So some of the facilities that we have here, and this is the gas turbine combustion, the setup that we are talking about. We are planning to do the OH radical visualization using the PLIF technique, and we have such we can investigate this type of phenomena in a gas turbine combustion. Okay, so coming to today's talk, so the contents are basically covered. It will be the trends and impact of CO2 emission on Earth, and then the carbon capture technologies that we have, and we will briefly talk about the methods for CO2 separation, and then we'll talk about the CO2 utilization. So you can note down your answer, or you can ask during the presentation, or you can ask me towards the end of this topic. Okay, so as we know that we need the energy for sustaining our day-to-day activities, and there are various sources of energies right now that we have. So the message is that all sources of energy will continue to be valid and necessary, and we need to go for a mix of energy. That is the demand of our. We should, I mean, as of now, we are using the fossil fuels, and the share of the renewable energy is continually going on the higher side, but still the fossil fuel is the use of fossil fuel is inevitable, and it will be continued to be used. So then what is the how we can mitigate the harmful effect of the fossil fuels? So the problem is that, I mean, we can try to capture the CO2, and we can basically use the CO2 for some downstream applications, or we can compress the CO2 and store underground for long, I mean, in the geological reservoirs. So we'll discuss some of these things in this presentation, whatever little thing I know. And this environmentally, it has to be sustainable. The energy, whatever you are using, that has to be environmentally sustainable and should be adopted in all sources of energy while using it. So this is basically the energy basket of India. You can see that we are in the electricity generated in India by coal, which is basically a lion's share that you can see. It's about 76%, and then you have the large hydro and the small hydro, then wind power, solar energy, the biomass, and nuclear, the gas, and the other things, right? So you can see that these are the coal is still being used as one of the major sources of energy in 2016-17. The data is not updated, but I believe that the renewable share has gone up, and I did not have a chance to update this, and but still the message is clear that the coal is still being used as a one of the fossil fuels for the generation of electricity, and it will be continued to be used. So then we need to make somehow clean coal, right? So that should be the objective, and we should reduce our CO2 emission to the atmosphere. So that should be the objectives in the next few decades. So installed capacity by source in India as on 31st January, you can see that the coal is about 58%. So these are basically the electricity generated, and this is basically the installed capacity. And you can see the large hydro, small hydro, all these things are here basically. The installed capacity is 58% for coal. Now, carbon capture, sequestration, and utilization. Okay, this is probably the one of the best solution to mitigate the global warming issues as per the IPCC's that is prediction. That is the rise in the temperature should be within 1.5 to 2 degrees centigrade. Okay, so that is the prediction given by the IPCC, and then we need to be well within this limit. So now we'll also see the effect of this the CO2 emission on various ecological things. But you can see here what we have to do is there are different sources which are emitting the carbon dioxide, and this carbon dioxide has to be somehow captured. And from this CO2 that we are capturing, we can make chemicals and fuels. Okay, that is basically called CO2 to X. X could be fuel or I mean other or any other. I mean it could be any fuel or fertilizer or chemicals. And the another part is that we need to do the carbon mineralization technology. Okay, so basically mineral carbonates that can be produced. And another thing is that we can store this carbon dioxide in the geological storage. Basically we can use for the enhanced oil recovery. Okay, so we can put this CO2, we can pressurize it and put it under the oil reservoirs, and we can basically mine the oil that was otherwise not mineable. Okay, so this is another area that can be pursued by using this carbon dioxide that we emit from different power generation utilities. Okay? So we can recover some of the oil. In fact, in US, some of the companies like Shell and Exxon Mobil, they are basically doing that. I think in the experimental basis. I'm not sure. Probably, I mean, if they are doing on the commercial scale, but I think they have tried. Another thing is that offshore CO2 storage in geological formations. So basically in the offshore rig, you have an offshore rig, and there you can basically drill a well, and you can put the CO2 under the bed. Okay, so that is basically another way to mitigate the CO2 emission to the environment. So now if you see that the anthropogenic factors that we have for the CO2 emissions are basically outlined here. So use of fossil fuel is about 87%, industrial processes and the land use. And now you have the different things like for the transportation sector, you have about 22% CO2 emission. For the electricity generation, it is about 42%. Industry is about 20%, residential is 6%, and any other factor is about 10%. Okay, so this is the typical distributions of CO2 emission from various sectors and industries. Now, the consequences of CO2 emission. So these are basically listed here. So increased concentration of CO2 in carbon sinks, and the global warming. Okay, now the global warming can affect the change in food supplies. It can cause extreme weather calamities, and the global average surface temperature rises by more than 1 degree centigrade, and the poor human health, rising sea levels. So these are some of the bad effects of the global warming. And increased concentration of CO2 in carbon sinks that can basically lead to acidification of the oceans and the carbon fertilization. So these are some of the consequences, harmful consequences of CO2 emission. Now, if you look at we are all hearing in the news and the other articles that the glaciers are melting. In fact, a few days back in the Uttarakhand, there was some the glacier related incident. So you can see here is a picture from 1941 August. This is called the Muir Glacier in Alaska in US. Here you can see the glacier quite well. And if I come to the next slide, you can see in the 2004 the same place looks very different. Okay, so all the glaciers are gone, and now you can see here a beautiful lake, but that is not needed. Actually, that is not good. Okay, so I mean it has basically the glacier got melted, and it is looking like this. So you can see that over the years, due to the global warming, some of the glaciers and various regions in the world has depleted, and that is not good actually. So if you look at the, some of the information I already gave, now you can see that the atmospheric CO2 level uh, is continuously rising ever since the industrialization. And you can see that this black line is the annual mean, and the red line is the lowest smoothing of 5 year. And you can see that the temperature is gradually increasing over the year. Okay, and now the temperature rise is about when it is basically coming to the 1 degree centigrade. And now if you look at the CO2 level at the atmosphere, you can see that the data is about 402.5 in January 2016, and then it is rising to 406 and 407. In fact, the CO2 level in atmosphere crossed the level of 400 in the year of 2016. Okay. So this is another consequence of the CO2 emission. You can see that the land and ocean temperature departure from average March 20, at March 2020. This is with respect to a 1981 to 2010 base period. You can see that the average temperature has is basically has increased in some regions of the globe, and it has decreased in some region of the globe. So this is again another harmful consequences. Here you can see that the annual global surface temperature change for both land and ocean. So it is seen that recently there is a very high uh, there is a steep increase in the annual change in the global surface temperature in both land and ocean. Okay. So these are some of the data that points out that harmful consequences of CO2. If you here you have the trends for CO2 emission over the years. So what you can see here in the CO2 in the ppm level, and it is for a long time. So these are the some of the data that I have taken from the internet, and you can see that initially that CO2 level was very small, and after post industrialization you can see that there is a rise in CO2 emission, and you can see it is approaching. In fact, in 2016, I showed that it has it has crossed 400 ppm level. Okay, so this is the yearly variation of CO2 concentration, which is in the recent year. This is for a long years. From 1000 to 2000, and now here you can see in the recently also you can see that it is clearly rising. Okay, so now we need to do something to arrest the such steep rise of CO2 emission. The average CO2 concentration in atmosphere is increasing at an alarming rate since the beginning of industrial age, and in 2016 it reached 400 ppm. It gone past of 400 ppm. So future trend predict that the CO2 concentration will continue to rise because of our dependence on fossil fuels as preliminary energy source. So now we need to think about the renewable energy source, and at the same time, if we are using the fossil fuels, we should try to use it in a better manner, meaning that we should use much energy efficient systems. We should go for hybridization. Like hybridization means that we can go for that IGCC plants, like the integrated gasification combined cycle, and we can also go for some of the new and better energy conversion systems like the fuel cells. So some of these topics are not discussed in this talk, but I hope that some of the experts will deliver some information on this. Like the fuel cell can be used, and it provides a better efficiency than many other turbo machinery or the diesel engine kind of things. And one can also go for hybrid mode, like one can use a fuel cell in the topping cycle, and then the bottoming cycle one can use a turbo machinery like the gas turbine cycle. So in that way the combined cycle efficiency will go up, and the net emission of CO2 in the atmosphere will decrease. Okay, so we need to attack this problem in several ways. One is that we need to go for better efficiency uh, uh, power generation system. We should go for hybridization, and at the same time, we should try to evolve our research towards capturing some of the CO2 that is being, emitted to the atmosphere, and we should use some of this CO2 to make some fuels and the fertilizers which we can use, and we can use this CO2 to we can store this CO2 and in the geological reservoirs. So that should be our approach, and I will try to talk about some of these things in this talk. So now, as you say that the average global temperatures have risen 0.75 degrees centigrade in the past 100 years. Now, can we predict that how much will the temperature rise in the next 100 years? So in the past 100 years, it has risen only 0.75 degrees centigrade. That means about a quarter degree centigrade. But can any one of us tell that how much it will rise in the next 100 years? Okay, so let us see. Yeah. So this is the prediction for rise in the temperature. And now if that happens, then it will be a catastrophe for the world and for the human civilization and all the animals and the ecology, right? So therefore we need to be very careful in our consumption, and we should try to, you know, go towards the better energy systems and mitigate the CO2 emission to a large extent. So as you see that the predicted impact, like we have seen that the temperature rise is predicted about 4 degree. Now, what will be the impact on us? So that we can see here. So if it is 1 degree centigrade, then we can see that the severe impacts in marginal soil region. Then the rising crop yields in high latitude developed countries if strong carbon fertilization. In the water, basically small mountain glaciers will disappear worldwide, and the potential threat to water supplies in several areas. If it is about 2 to 3 degrees centigrade and the 4 and 5 degrees centigrade, you can see that all these things are listed here. So rising number of people at risk from hunger, which will be about 25 to 60% increase by 2080s in one study with weak carbon fertilization, with half of the increase in Africa and West Asia. Okay, significant changes in water availability. So it's one of the study projects that more than 1 billion people suffered water shortages in the 2080s. Many in Africa, while a similar number will gain water. Greater than 30% decrease in runoff in Mediterranean and Southern Africa. So if it is about 4 degree, and then entire regions experience major declines in crop yields. Okay, so yields in many developed regions will decline even if strong carbon fertilization. So sea level will rise. The rise in sea level will threaten many world cities, including London, Shanghai, New York, Tokyo, Hong Kong. Okay, so these are the predicted impact if the temperature rises at about 4 degree and higher. Okay, so this is from a data on the economics of climate change. It's quite old, 2006, but this will give us some of the ideas. Okay, so what will happen in the ecosystems? So in the ecosystem, many species will face extinction. Okay, extreme weather events. So there will be rising intensity of storms, forest fires, droughts, flood, and heat waves. And the small increase in hurricane intensity will lead to a doubling of damage caused in the US. Okay, so and also in other countries also. A risk of rapid climate change and major irreversible impacts. So risk of weakening of natural carbon absorption and possible increasing natural methane releases and weakening of the Atlantic TSC, onset of irreversible melting of the Greenland ice sheet. So these are some of the things that is going to happen if, with the rise in temperature. So the conclusion of the climate change is that the CO2 concentration is the highest in last so many years. Warming of the climate system is unequivocal. Most of the global warming of the past half century is due to the increase in the greenhouse gases. Like so CO2 is a greenhouse gas, and so is methane, right? Global greenhouse gas emissions reduction challenge. So basically, we have to stabilize the CO2 concentrations at 450 ppm. Now we are already about 410 ppm. So in order to have a temperature rise limited to 2 to 2.4 degrees centigrade, we should limit the CO2 concentration at 450 ppm. So peak CO2 concentration is before 2015, and the reduce emissions to 50 to 85% of 2000 emissions. So whatever CO2 is emitted at 2000, we have to reduce the CO2 emissions to 50% to 85% in that by 2050. So we have a taller task, and the governments across the globe are working towards that. And here in India also, we have done lot of way to mitigate the CO2 emission. Now reduce annual global emissions to 5 gigaton in long term. Okay, so that is these are the targets that we have to have. Now in US, this is the energy profile of the US. You can see that the global carbon dioxide emission from electricity in 2007 is about this. And you can basically see that the percentage of different things here, right? So in the coal is about 76%, and natural gas is 14%, fuel oil is 9%, and other is 1%. Okay, so in quad of BTU, you can see that the coal is still rising, right? So use of coal is rising, oil is rising, natural gas is rising. The renewables has risen, but it is far less than this. Okay. So now emission mitigation potential that we can look at. So if you can see that there are different things that is listed on the right. So emissions to the atmosphere is basically under this curve, and now you can see that the coal to the CCS, the potential for the carbon capture and sequestration, that potential is basically marked by this. Okay, so we are somewhere here in 2020, and now you can see that the potential of CCS is not being utilized. It is very small, and you can see coal to gas substitution. So if we substitute coal by gas, then you can see that there is also a chance of reasonable mitigation of CO2 emission. If we are going towards the nuclear, again, we can save some of the CO2 emission. And if we go to the renewable energy, again, we gain a lot of, we mitigate a lot of CO2 emission. And the conservation and energy efficiency, right? If we are using higher efficiency energy systems, or even the LED bulb now we are all using. So we have to find basically the better energy systems, and then we should conserve the electricity by going for high electrical rating equipment and the devices. Then we can again save a lot of CO2 emissions. So these are the way that we can mitigate the CO2 emission to the atmosphere. So it is seen that at this moment our effort is very small, and now if we go towards 2050, we can see that the CO2, the carbon capture and storage is potential has risen, and then some of the coal is will be substituted by the gas, like the natural gas, and you can see the renewable energy is growing, and then the conservation and energy efficiency is better, getting better, right? If you go towards 2080, and you can see that the CCS has the data from this IPCC report, it is showing that the CCS will become more and more useful in that time. So now the question is that why the CCS is not being used at this moment? Because actually the CCS involves cost. We will come to that later on. And if we can do some research, and we can find a better way to reduce the cost for the CCS, and then we can probably use that. And apart from the cost, it should also come from the government policy. The government policy in the coming years will probably be more stringent on the emission side, and then um, uh, it will be forced on us to use the carbon capture and sequestration strategy. So I foresee that in coming years that CCS will be very much a solution to mitigate the CO2 emission, and the government agencies will enforce on us to absorb some of the increased cost uh, coming out of the CCS. For example, now if the electricity cost is about 5 rupees, and then with the CCS it might be at this stage it will be about 70 or 80% more. Okay, so if we are taking 1 unit of electricity from a power plant, if we are doing the CCS, the cost of electricity will increase by 70 to 80%. So 5 rupee per unit will basically be about 8 to 9 rupees. Okay, so the consumers are not willing to pay at this moment, and maybe there is not much awareness that was developed among us. And but in future, the government will there will be probably a policy to mitigate this CO2 emission, and the group of nations are working on this, and hopefully will go towards that. Okay, so now I will come to the different CCS overview, like the capture plant, capture of CO2. So CO2 can be captured from the power plants, from the natural gas treatment and the oil refineries, from all any other industries, right? It could be a steel industry, it could be a cement industry. You can basically capture CO2. Now, after capturing, what we are going to do? We can transport the CO2, and the transportation can be done by using pipelines or ships. Okay, so and then the sequestration. So sequestration can be done in the geological formations, like in the underground or in the ocean. There are some reservoirs. You can basically, there are enough reservoirs to store the CO2 that we are emitting to the atmosphere. Okay, and the utilization, right? So some of this captured CO2 can be useful to can be used to produce alternate fuels, which can be useful for the transportation purpose. Okay, this could be that methanol, or it could be the dimethyl ether. Okay, so this, or you can also produce natural gas like methane or CH4 from this captured CO2. Okay, and we can also produce fertilizers and other chemicals. Okay, so there are some of the industries which are currently utilizing CO2, but the scope is there is a lot of scope. So if we can reuse this CO2, and then it will reduce the emission to the atmosphere. So these are some of the overview of the CCS. The carbon capture and storage market size exceeded US dollar 3 billion in 2019, and its cumulative capacity is anticipated to be exceeded by 124 MTPA by 2026. Okay, so there is a huge scope for this carbon capture and storage market, and you can see the timeline here. So in 2019 it is more than 3 billion, and by 2026 it is going to be double, right? So the CAGR comes out to be about 5.4%. So now this whatever the carbon capture is there, so we are having about 5%, less than 5, I mean the greater than 5% for the from the post combustion. Now the pre-combustion is greater than 64 MTPA, right? That is the market size in 2026. Now, what are the growth driver? So burgeoning demand for CO2, enhanced oil recovery techniques. As I said, that some of the US-based companies, or even in the Norway, some of the companies are getting this CO2 and they are putting it under the oil well for the enhanced oil recovery. And they're using the North Sea in Europe. In the North Sea, they are basically, they have developed, I think Norway has developed a rig where they are basically doing this CO2 based enhanced oil recovery. Stringent government regulations towards GHG emission, greenhouse gas emission. That is what I said, because we all have to be aware, and then the government regulations in this in this regard will come sooner. Increase in investment towards government funded projects. Okay, the government will basically support some of the high cost projects, and these are the growth drivers. And it will also create a lot of job opportunities by creating a sector which, I mean, it could be useful in any industry, like as I said, the steel industries, cement industries, and the power generation utilities. So everywhere there will be a need for this, and there will be a lot of scope. Pitfall is obviously the high installation cost is the pitfall, and then the cost of electricity or power, you can say, that is also uh, at this moment it is high. But I think with research, with time, the cost of CCS will come down. For example, we have seen the cost of solar cell has come down significantly with research. Similarly, the cost of fuel cell is also on the decline over the years through research. Okay, so similarly, the if the research community is aware, and then we are developing new technologies in this regard, then the cost of the installation cost and then the operation cost can also come down. Okay. Now I will give you some technology overview of the carbon capture options. So CO2 can be captured by any one of these method, like the post-combustion capture, like pre-combustion capture, oxy-fuel technology, and then the different industrial processes. Right, you can get it from the cement and the steel industries. Now, post-combustion capture means that you burn already the fossil fuel and you recover the carbon dioxide from the flue gas. Okay, so that is the post-combustion capture. Pre-combustion capture is that where you are basically before the combustion you are getting the CO2 separated from the gases, from the fuel. Okay, so what do you do in the pre-combustion? It could be basically a gasifier where you can gasify coal, and you can produce the synthetic gas, and from that synthetic gas, which is a mixture of carbon monoxide and hydrogen, you can do the water gas shift reaction, and then you can produce the a stream of CO2 and hydrogen. Okay. Can you please mute yourself? Okay. So from the syngas, one can recover hydrogen via water gas shift reaction. So all the carbon monoxide will be converted to CO2, and the steam will be converted to basically H2. Basically, CO plus H2O is going to CO2 plus H2. So that is the reaction that takes place, and it is possible to produce a mixture of CO2 and H2 from gasification, and then you can separate the CO2. And there are different techniques for CO2 separation. So I will discuss some of them later. Okay. Oxy-fuel combustion is a very promising technology, and in my opinion, it can be very useful. But there is a need for separation of oxygen before the air is from the air before we burn the fuel. Okay, so from air we need to separate oxygen and nitrogen. Basically, you separate nitrogen and you can throw it, and then the oxygen, fresh oxygen, you have to get, and then you burn fuel, like it could be natural gas or coal, and then in that process you will be able to generate a stream of pure CO2. Okay, so if you are burning natural gas, which is methane, the flue gas will be having CO2 and H2O, and then you can basically condense the H2O and separate it out, and then the rest of the gases will be CO2. It will be having a very high purity CO2, which is good for the downstream applications, or you can sequester. Okay, so in oxy fuel you can basically do that, but it comes with a challenge, because you need to separate oxygen from air. Okay, so there you need to use some technologies like the cryogenic technology or the PSA technology to separate oxygen from air. Okay, and which basically increases the uh, which reduces the efficiency of the plant. Okay, so that is one of the concern. Now, CO2 separation technologies could be based on the solvents. It could be aqueous, amines, and salts. It could be membrane-based separations. Like, for example, when I say that if we have CO2 and hydrogen from the pre-combustion capture, we can produce CO2 and hydrogen, and we can separate hydrogen based on the membranes. Okay? Now, this could be polymeric membranes or the ceramic membranes, okay, or the metallic membranes are also possible. Okay. So by membranes, you can separate the lighter molecules, that is hydrogen, and the rest of the gases will be the CO2 then. Okay. So in that way, one can produce a very high concentration of CO2. The third step is the solid sorbents, like it could be the lime, zeolite, or activated carbon, which can basically absorb the CO2. Okay, and then you can heat it and you can get the CO2 separately. Okay, so in that process also one can capture CO2. So cryogenic process involves the liquefaction or the distillation. So that is also another route of CO2 separation. So I will not be able to go through all of them, but I will discuss some of the things subsequently. So post-combustion capture, where you are basically using the fossil fuel, it could be coal, gas, or even the biomass, which is a renewable fuel. You can use this and you can burn in air to produce the heat. And then from that, you can run a turbine to produce power. And then the flue gases, you have to separate this nitrogen and oxygen, because most of the time we give surplus oxygen in air in the boiler basically, and then you need to separate this nitrogen and oxygen, and then you can basically separate CO2, right? Of course, there will be other trace elements which are the impurities that will be there. Then you need to also develop a way to separate them. Okay, then but essentially you need to separate a large amount of nitrogen and the oxygen. Okay, because air is having 79% nitrogen by volume, so you need to remove a large amount of nitrogen and some amount of oxygen from this flue gas, which is a very not so very easy task. But yes, there are some of the techniques that I discussed previously that can be employed to remove CO2. The problem is that those type of reactors for separation of CO2 will become very bulky. Okay, because you have to deal with a large amount of volume of flue gas. Okay, so that is one of the disadvantage of the post combustion capture. In the pre combustion capture, what we do, we basically take coal and biomass and then gasify it, okay, in presence of either air or oxygen or steam. You can gasify coal or biomass, and then we can do the reforming, right? As I said, that water acid reaction, where you can basically reform the syngas, and you can produce hydrogen and CO2. Okay, now you can basically remove the CO2, and you can compress, and you dehydrate, and it is ready for the downstream sequestration or utilization. And this hydrogen which is produced can be used to produce heat and power, right? So this hydrogen can be useful to operate a gas turbine, right? You can directly use this hydrogen to run a gas turbine, and or you can operate a gas turbine, steam turbine combined cycle, right? Also, this hydrogen can be used to produce electricity based on a fuel cell, which does not involve any rotating part. Okay, yet the efficiency could be high, but the fuel cell cost is currently very high, and over the year it should come down. And then this hydrogen can be directly used in the fuel cells, and it can also be used in the gas turbines, right? You can store this hydrogen also. So that is the beauty of the pre-combustion capture, where you can separate the CO2 much easily, because hydrogen is a lighter molecule, and membrane-based techniques can be employed easily to separate hydrogen from the stream of hydrogen and CO2. Oxy-fuel combustion, as I said, it involves the separation of air separation unit. Okay, there the air will come and it will you have to separate nitrogen from this, and oxygen will basically go to the boiler where you are supplying coal, gas, or biomass, boiler or the combustor, and then you can produce CO2. Right, this will be a pure stream of CO2 that you can produce directly. You do not need any separation technique. Where in the former one, in the post combustion and the pre combustion, you need a separation of CO2. But here it does not involve separation of CO2, but it needs separation of oxygen, right? So you separate oxygen from air in the beginning, and then you get a pure stream of CO2. So there are other industrial processes. There also you can capture CO2. And after capturing the CO2, what you have to do? We need to compress it. Okay. So another thing is that if one can compress it and then do the phase change and make it in the liquid state. Okay, and then you can pressurize it and store it at a high pressure. Okay, so compression and dehydration, that is the next task that one has to do. Okay, and this CO2 can be stored as a liquid at high pressure. Okay, and you can also put this CO2 under the geological reservoirs. So this is the a schematic diagram of the post combustion capture, where basically fuel and air are used to burn, and the heat is generated, and that is used to produce the power, and you have to separate the carbon dioxide from the other gases. Okay, so this is the post combustion capture. Now how the separation is done? Basically the flue gas is coming into the absorber unit. Okay, where you have some solvent, which is basically then an amine based solvent, which is recirculating, and this amines will absorb the CO2, and then it will this rich mixture will come to the heat exchanger. There will be a heat exchange between this stream and that stream, but this finally this rich mixed solvent will come to the stripper unit, where you basically use heat to remove this CO2 from this solvent, and then you can get a stream of pure CO2, right? And then this lean mixture can come to the heat exchanger, because it is at a higher temperature. It will reject heat and it will come to the absorber, and at the same time the rich mixture will get heated up when it is entering the stripper unit, right? So that is the schematic layout of how to separate CO2 from the flue gas. So it is done using a recirculating amine based solvent. Okay, yes, so this is the one. Now here you can see a schematic of the post combustion capture. As I mean, so sorry, this is the oxy, the title is wrong. This is basically oxy fuel combustion. So what you have here is an air separation unit, and then you separate oxygen from air and send it to the boiler, right? So when you are doing this, when you are firing coal, there will be CO2 that will be produced. Okay. Now, since you have removed the nitrogen from air, the temperature inside the boiler or the furnace can go very high. Now, in order to do that, you need to mix recirculated flue gas. So some of the flue gases you can get back from the downstream, and then mix it with the oxygen. Okay, and then you can send it to the boiler. So that way you can restrict the rise in temperature inside the boiler, right? Because you are substituting the nitrogen by CO2, right? Okay. So this CO2 will then go to the filter, and like the back filter, whatever we have. This is the almost the same power plant that we have seen, but here you need to fit an air separation unit, and then you have to get the recirculated flue gas. Then you will be able to capture CO2 from this, and then the water can be condensed here. Okay, and you can separate water, and you have the FGT unit, flue gas desulfurization unit, where you can separate sulfur and other heavy metals like the mercury, etc. You can separate. Okay, and then rest of these gases you can compress. Okay, so this is the CO2 capture and compression unit. So you basically clean this CO2 and then you compress it, okay, and you store it. Now this compression involves a cost, obviously. So here you need a here the operating cost increases. Also the installation cost will also increase. In the air separation unit also you need to put an air separation unit. The operating cost and the installation cost will also increase. So that is why at this moment it is not very much suitable for the economical applications. So what can be done instead of the air separation unit based on the cryogenic or the PSA system? One can use a membrane-based separation system, and one can develop membranes which are effective and which can separate oxygen from air. Okay, so there has to be some research on that direction for large-scale separation of oxygen using membrane. So I know one professor from MIT was doing research on this topic. He gave a talk few days back at our department. So he was mentioning that there is a possibility of separating oxygen in a large scale based on membrane technology. So therefore, I think research has to be pursued in that direction. Yes, so we are all knowing about this pulverized coal plant, right? So here you are capturing the CO2 after the combustion, right? So this is the post-combustion CO2 capture. So we have the pulverized coal boiler where you are supplying coal and air, and then you have the ESPs and the FGDs, etc. And after that, the CO2 capture system is placed where you are separating the CO2 based on the amine-based separation, right? So that I discussed previously. Now this is the post-combustion based IGCC plant, right? So what is happening here? You are supplying air through the air separation unit, right? Or you can provide steam also, right? You need not provide oxygen. You can also provide steam, and then you can basically gasify coal. Yeah, I think steam is given here. So you are gasifying the coal, and then after that there are quenching and other shift reactor. So in the shift reactor you are again giving steam and then converting it to CO2 and hydrogen, and you have to remove the sulfur and the other trace materials, and then you capture CO2. Okay, so now this CO2 capture could be based on a selection based CO2 separation, and then the hydrogen can be obtained, and then this hydrogen can run a gas turbine based combined cycle system. So that is the concept of the integrated gasification combined cycle system. Now when you do this, your efficiency will increase, right? Because it's a combined cycle operation. You are gasifying coal and running a gas turbine. Coal cannot be used for running a gas turbine directly, but here you are gasifying coal and you are using the gasification product, that is the hydrogen, to run a gas turbine. And at the bottom of the gas turbine, you have a steam turbine. So the combined cycle efficiency will be higher. Okay, and the net penalty will not be that much here when you are going through the IGCC plant. Okay, because you are making the coal. I mean, of course, there will be a net gain itself because you are running a combined cycle plant and you are using coal as the fuel. Okay, not the natural gas. Okay, so that is one of the way we can use coal in a better way. Okay, but the problem lies in the gasification technology. As I said, in India we have a very high content of ash in our coal, and if they are not directly suitable in the gasifier, those are commonly available in the Western world. Or I mean, there are the gasifiers which are based on the entrant flow gasification technology, where you can use coals which are having very low amount of ash. Okay, so Mitsubishi has developed the entrant flow gas gasifier, etc. And then we cannot use our coal directly in those gasifiers because we have a lot of ash. Now in entrant flow gasifier, the reactor temperature is very high, and at that temperature, all the ash will melt. Okay, and it will form agglomerate, and it will be very difficult to remove. Since we have a very large amount of ash, it will be a very much difficult to use internal flow gasifier based on our coal. Therefore, we need to basically develop a fluidized bed system where we can facilitate periodic removal of ash from the gasifier. So that is why I think I was interested and I got interested and I wrote this project on the dual fluidized bed gasification system. And if it is successful, then we have developed this gasifier, which can operate at about 100 kg per hour of coal. And once it is demonstrated, then probably that technology can be made available to run on our own indigenous coal. Okay, and it will be an indigenous technology based on high ash coal that we can operate. So this IDCC is a very promising aspect, and if we can develop a very good gasifier which is stable and which is suitable for this purpose, then it will result in a very high energy efficiency compared to the pulverized coal power plant, right? Compared to the PC plant, right? Pulverized coal plant, it will be much higher efficiency because you are using a combined cycle. And at the same time, it will also offer us a benefit to separate CO2 from the gasification process, right? So you can capture CO2 from this also. Now, the CO2 separation technologies can be many. So some of the technologies are basically mentioned here. Separation with sorbents or solvents. So suppose this is the gas A, which is having CO2, and now this is one of the reactor where the solvent is going and it can capture the CO2. So that mixture will basically come here, and here the solvent will be regenerated. And for the regeneration, one can use the waste heat available in the plant. So for example, the deboiler, etc. And you can use the waste energy and you can produce CO2, and then this solvent will again go to the CO2 capture unit and capture CO2. So there will be a cycle like this. So in this way, one can easily capture CO2 based on solvents. Okay. Another CO2 separation technology, as I said, is based on the membrane. Okay. So here we have a gas with a CO2, and now based on membrane, the membranes can separate CO2, and you can get the flue gas, basically the other parts. Okay. So this is basically the membrane based separation technology. Another is the separation by cryogenic distillation, right? So here basically the gas is coming and now you have to compress it. Okay. And then you can do the distillation, and you can basically just on the cryogenic condition, and you can separate gas A and the CO2, right? So what will happen at that at the cryogenic distillation? Basically, that CO2 will get condensed, and then the rest of the gases will come out. So this will again, because you require power here, okay, and you need to maintain the cryogenic condition. So it is having a lot of energy penalty. Okay, so solvents or solvent-based approach is, they have been demonstrated quite well in last couple of decades, and also the membrane-based separation technology is coming up. There are a lot of research that is going on across the world, and this is a promising technology not only to separate CO2, but it can also be useful to separate oxygen from air also. Okay. Yes, so this is the CO2 capture unit. As I said, that the flue gas can come, that will typically have a 10 to 15% of CO2, and here the solvents, okay, that will come through the cooler, and it will be dropped like this, and there is the absorber where basically this solvents will absorb the CO2. Sorry. And then the remaining gases will leave through the stack, and then the concentration of CO2 here, it can decrease up to 1 to 2%. So 10 to 15% to you are decreasing to 1 to 2%. And then the solvent, which will become CO2 rich, that can go through a heat exchanger where it is being heated up by the returning stream, and then it will go to the stripper. The stripper, you can basically strip CO2 and here you are using the waste heat from the deboiler to generate CO2. And in this way, you can generate CO2 which is about 99% pure. The capture cost of CO2 is about 80% of the CCS cost, and rest of the 20% accounts for compression, transportation, and sequestration. The solvent regeneration cost accounts for about 60% of the capture cost. Okay, so you can see that the solvent regeneration cost is quite high. It's about 60% of the capture cost. The cost of electricity can increase by 70 to 80% based on that MEA. MEA is one of the amines, and based on the MEA, the research has shown that the electricity cost will rise by 70 to 80% if you want to capture CO2. Okay. So now CO2 capture technology selection. Here basically how you will select the technology, drivers for process selection, like the temperature of the feed gas, presence of oxygen, presence of contaminants like the H2S, ammonia, COS, sulfur dioxide, etc. It should be commercially viable, cost effective, and can be assimilated in existing process configuration. Right. So we have a power plant, and now if we can retrofit, or we can develop another system to capture this CO2, that will be good. Okay. So all these things need to be considered before coming to a technology. So possible technology routes could be, as I mentioned, the gas separation membranes, absorption membranes, physical absorption, cryogenic separation, adsorption, and the chemical or amine based absorption. Okay, so these are the CO2 capture technologies. Okay, so chemical absorption process is extensively used for CO2 removal from the flue gas and industrial gases, and wide choice of amines commercially available, for example MEA, DEA, etc. Okay, some of the blended amines are also available. Thermodynamically non-ideal system due to electrolytic dissociation of CO2, amine, and water. Poor stage efficiencies in the contractors due to heat of absorption. For effective modeling and engineering design of amine contractors, one need to look at the thermodynamic interactions. Okay, so I will not go into much of the details of this, but this is an overview that I'm trying to give. So these are the different kinds of amines can be used, like monoethanolamine and dicycloamine and diethanolamine, etc. So these are the typical amines that can be used. And I'm not an expert of this topic, so I will not be able to tell you much about this. Okay. So cost of post-combustion CO2 capture, if you see that this is based on a study done by one US-based agency. So you can see the overnight capital cost. These are for different things. One is the ultra supercritical coal power plant. Another is the ultra supercritical coal with 90% CCS. Okay, so here you can see that the capital cost has increased. Okay, and now per megawatt you can see the capital cost has increased. But if you compare the capital cost with the onshore wind and the solar PV, that is very high, right, at this moment. Okay, because this plant itself is very the plant capital cost is also very large. Okay, now fixed operation and maintenance cost, it's about 42,100, and here it is 80,530 per megawatt year, which is again very much higher than the solar PV and then the onshore wind applications. So the total here you can see the CO2 transport and storage cost is basically 9.13 megawatt hour, and that levelized cost you see that has gone up from $92.46 to $151.34. So that means per megawatt hour the cost has increased. Now this is now does not look lucrative when we see the data from the wind and the solar PV applications, right? Okay, so but one thing we have to consider that the solar PV and the wind is have a lot of variability during the day. Okay, and one needs to store this solar PV, whatever power is produced in the battery, so that one can use it in the night. Okay, so that problem is not here. So therefore, I think the battery cost, I mean, it involves some of the cost due to the battery storage, and also the environmental damage due to potential due to batteries also. Okay, so therefore we need to be very cautious, and I think with research, if this cost can come down, then therefore then it will become suitable. Okay, so I'll skip some of these slides in the interest of time. Now, I already described the oxy-fuel combustion process. Again, I will skip this. The pre-combustion capture, I already mentioned some of them. So here, what I mentioned is that it involves the sequestration of CO2 from fossil fuel prior to completion of combustion. So you do not burn the fuel, rather you gasify, and then whatever gases are produced, that is the syngas, before it is burnt, you capture the CO2, right? So here is a schematic where you have the gasifier, where you are supplying the fuel and steam, and you may supply oxygen also. Then the syngas will not have any nitrogen dilution because you are not giving air. Okay. If you are using a dual feed-based bed gasifier, then we can gasify coal in a pure steam media. We do not need to give oxygen or air. But in some of the gasifier, to sustain them, uh, you need to produce some of the heat, because the gasification reactions are endothermic. Therefore, you need to supply some external heat. Now, in the dual fluid bed system that I initially discussed, there you are circulating heat via bed materials, right? But if it is a only single reactor, like a bubbling fluid bed reactor or circulating fluid bed reactor, you need to burn a part of the fuel inside the reactor, and for that, if you are using air, your gasification product will have nitrogen. Okay, and now again you will have the same problem of separating large amount of nitrogen from the syngas. Okay, therefore the dual fluidized bed system is better, because here in one reactor I am gasifying the fuel in presence of steam, in another reactor I am burning the coal in presence of air, and I'm transferring the heat from one reactor to another reactor. Okay, so that is the advantage of the dual fluidized bed system, and this syngas will be free of nitrogen then. Okay, and after that you can basically remove the particles through that is basically the ash from the cyclone, and then the rest of the gases can be fed to the water gas ship reactor, where you're producing the carbon dioxide and hydrogen, and then you have the desulfurization column where you are separating sulfur, and then you can capture the CO2 and you can store it, and the rest of the gases is hydrogen, which can go to the gas turbine. So that is the pre-combustion capture, and by basically designing the gasifier in such a way that you can prevent the nitrogen dilution, and then you will not be able to you do not need to separate nitrogen. Okay, so that will be quite good actually. Okay, so this is again another layout of this pre-combustion capture, where you can have the raw syngas produced by the gasification, and then this raw syngas can be cleaned, and after cleaning the raw syngas, you can send the clean syngas to the combustor of a gas turbine, where you are getting the ambient air compressed, and then you are burning the fuel to produce high temperature gas, and then you have the turbine to produce electricity, and then you have the heat recovered steam generator, which produces the steam, and you can have a Rankine cycle here. So it's a combined cycle plant, like IGCC plant that I was discussing, and you can also separate CO2 from this plant and store it. Now, pre-combustion capture, it comes with the advantages, because generation of hydrogen or synthetic gas as alternative fuel. So you can either use coal and biomass, and you can produce hydrogen or synthetic gas, which is an alternative fuel. Compact system design due to lower gas volume, higher pressure, and higher carbon dioxide concentration. Okay, but the problems are there. it requires high auxiliary systems requirement, reduced efficiency due to hydrogen fuel gas turbine application. Okay, limited commercial availability of IGCC technology. So it is not commercially available. Although in our country, BHEL has done development of IGCC, and they have also done the development of a gasifier, but it is not available commercially. But with it requires, that means it requires more emphasis on the research side, and after that, I think it will be suitable for the commercial applications. Now, again, in the pre-combustion capture, there are various technologies to separate the CO2, and these are basically one is called the sulfinol method, okay, where basically different chemicals are used. Another is the Selexol method and Rectisol method. So these are the different way of capturing CO2 from the pre-combustion capture. Okay, before you burn the fuel, you have to capture this CO2. Physical absorptions becoming increasingly popular as gas treating solvents, especially for coal gasification applications. Physical solvents tend to be favored over chemical solvents when the concentration of acid, gases, or other impurities is very high. Okay. In addition, physical solvents can usually be stripped of impurities by reducing the pressure without the addition of heat. Okay. So I will again skip some of these slides for the interest of time, and I will come to the next discussion, which is basically the CO2 capture from industries. Okay. So as I said, that there are different industries which are emitting a lot of CO2, and here is a data in 2017 that how much CO2 is emitted from each one of these industries. For example, iron and steel, it emits about 3.1 gigaton of CO2 per annum, and it uses only 4% energy from renewable sources, right? Chemicals and petrochemicals, the share of renewable energy is only 3%, and it emitted 1.7 gigaton of CO2. Cement and lime, again, it emitted 6%. It used 6% renewables, and they emitted 2.5 gigaton of CO2. So these are the three heavy industries. And on the other side, if you look at the road freight, aviation, and the shipping, there are very small or negligible amount of renewable share, and they also emitted CO2, which is about 2.3 gigaton of CO2 or 0.9 gigaton of CO2 for the aviation and the shipping industries. Okay, so therefore, in long run, the road freight, aviation, etc., is bound to increase, and therefore we need to focus on CO2 capture from these industries or using the renewable energy in these industries. Similarly, the construction sector requires iron and steel, and again, the emission from iron and steel is quite high, and there has to be, I mean, we should pay attention to these sectors to either operate it through renewable energy or reduce the CO2 emission, and it is possible to do that. So I will give you some case study here from CO2 capture from cement industry. Okay, so here you can see you have the raw materials, energy, and resources in the quarry, and then the crusher, and they are being transported to the raw mill, and then there is a kiln and preheater and pre-calcinator, right? This is the thing. Then you have the cooler, and after that you have the cement mill, where basically you crush the cement and then you store it, and then the logistic means that you transport the cement from one place to another place. So now here you can see that the contribution from each of these processes, how much energy is needed and how much CO2 is emitted. So you can see that these are small numbers otherwise in comparison to this number, right? So in the kiln and preheater and pre-calcinator, you are using 3,150 megajoule per ton of energy, and you are emitting about this much kilogram of CO2 per ton. Okay, so if we can try to make it renewable, and or you can capture CO2, then I think it will mitigate a lot of CO2, right? And this is possible. So I do not have another slide to describe how it can be done, but I can discuss it orally. So in a cement industry, what we do, we have the calcium carbonate, that is a limestone. Okay, and then this limestone decomposes into calcium oxide and it releases CO2, right? It is possible to capture this CO2, but the only problem is that in the clean we are using air. Okay, now air is used to burn some fossil fuel, and that produces a very high energy where this calcium carbonate and then the decomposition takes place, right? So now instead of air, if we can use oxygen from an air separation unit, okay, and this oxygen can be diluted with the flue gas, and we can use it here in the clean, and also the calcium carbonate will decompose into CO2. Therefore, it will produce a pure stream of CO2, and then this CO2 can be cleaned from any contaminant. There will be no other gases like nitrogen here. Okay, so it will be possible to capture CO2 from this gas very easily. Okay, and another aspect could be that you can have a solar PV plant or solar thermal plant or whatever, and the excess electricity one can use to split water to produce hydrogen. And now using this CO2 and hydrogen, one can produce methanol or DME or natural gas. Now these are the renewable fuels which can be used in the IC engines for the transportation purpose, right? So that could be one of the way to somehow decarbonize the cement industry. Okay, so I think there has to be research in that direction. Some of the European countries are doing research in this area. I've seen some of the papers in that direction they are working on, and it is possible to produce methanol from this CO2 captured from the cement industry. Okay, so this is another layout where this is demonstrated. I'll skip it. Now, decarbonization of iron and steel industries. Okay, so it may be also possible to decarbonize the iron and steel industries. In fact, Tata Steel is doing some research where they are developing a gasifier where biomass will be used to produce syngas, and based on this syngas, they are going to operate the blast furnace. Okay, now in the blast furnace, in the current conventional blast furnace, they mix the fossil fuel and then the burn in presence of air. Again, from the flue gas that is coming from the blast furnace, it may be possible to capture CO2. Okay, so that CO2 rich gas we can separate based on any of the techniques that I discussed earlier in the previous slides, and it may be possible to use the CO2 rich gas for sequestration or utilization. Okay. Now, carbon transport, basically the CO2 transport. So, in the US, I think there are 2,500 kilometers of pipeline in Western US, and the use of existing infrastructure, it requires dry and sweet gas to prevent corrosion. Okay, so that is one thing that we have to keep in mind. Challenges are manageable, and it is similar to transport of hydrocarbons. So we can have a CO2 pipeline, and then we can bring the CO2 to the location where it can be sent into the geological reservoir. So big picture is the storage in oil reservoirs, and that is for the depleted and enhanced oil recovery. Natural formations and the ocean storage can store a lot of CO2. The question is that will it leak? It may not leak. Okay, models suggest 99% containment. So once it is sent into the geological reservoir, it will diffuse into the pores of the rocks, and then it will remain there. Okay. Existing reservoir data can be used to estimate storage potential and address the water concerns, and no groundwater contamination. Okay, so I think the geologists are working on this direction, and they're doing a lot of experiments to see that how much containment, and based on the imaging, etc., and then they're predicting whether it will contaminate the groundwater, etc. So some work they are doing. Now CO2 utilization, this is the last aspect, and here I am going to cover that how we can utilize the CO2. So before that, hydrogen is one of the renewable energy carrier, and if you see that in this budget also, the finance minister has discussed about the hydrogen economy, hydrogen, and I think she has declared there will be some initiative from the government on this side. And so one is that hydrogen is not, we can, is a fuel. It can be used as a fuel, but it is not readily available, right? Like natural gas is available, it can be it is mineable, coal is mineable, but hydrogen gas is not available. So hydrogen is basically a carrier. Okay, so what we do, we can produce hydrogen from various other resources. Like we can use biomass, we can gasify and produce hydrogen. Okay, and we can capture CO2 and store it. Similarly, we can gasify coal, and from that we can produce hydrogen. We can use natural gas, and from the natural gas, by deforming, we can produce hydrogen, and CO2 we can capture. So we can produce hydrogen from various sources. Okay, but if we emit this CO2 to atmosphere, then it is not useful actually, right? Then it is as good as using the coal, right? If we are just emitting this CO2 to atmosphere, right? If we are capturing this CO2 and storing it, then it is good. We are not emitting this CO2 to atmosphere. Okay, so by gasification, we can produce hydrogen. Also, if we have excess electricity, instead of storing in large scale batteries, which is also costly and not environment friendly sometimes, then we can use this excess energy to split water and produce hydrogen. Okay, so infrastructure, and then we can basically capture this hydrogen and store. So hydrogen can be stored at very high pressure in cylinders, and then based on the requirement, we can use it either for the power generation or the mobility, or basically transport, etc. Right. So hydrogen is a renewable energy carrier, and if we are producing hydrogen from biomass, then it is absolutely renewable, right? If you are producing hydrogen by electrolyzing water, when the electricity is coming from the renewable energy, then it is a renewable hydrogen, right? If you are using coal to produce hydrogen, then it is not a renewable hydrogen. But if we are capturing this hydrogen, if you're capturing the CO2 from this coal and storing it, then it is better. Okay. Similarly, from methane, one can produce hydrogen, and methane has a very high H/C ratio from other hydrocarbons, right? The H/C ratio is basically 4:1. Okay, so therefore the methane has a lot of hydrogens, and you can basically capture hydrogen, and the CO2 you can sequester. So the main message is that the hydrogen is a renewable energy carrier, and another thing is that you can combine this CO2 that you are capturing from various sources, and you can store it as a fuel. So how it can be done? If you have excess electricity, you can electrolyze and produce hydrogen, and from the flue gases you can capture CO2, and then this CO2 and hydrogen you can do a reaction. It is called methanation, right? It is called methanation, and by methanation you can produce methane. Okay, now this methane is a natural gas, which is also a very clean fuel otherwise. Okay, because it is having a 4 hydrogen atom and 1 carbon, right? So it is a very clean fuel compared to any other hydrocarbons. So you can basically capture this CO2 and store this hydrogen. So you do not need a very high pressure storage for the hydrogen. Rather, you can use this hydrogen to produce methane. And now this methane can be stored, or you can make methanol, which will be a liquid fuel, and you can store it. And that can be used for the different sectors like residential, transport, and the industry. Okay, so this is one of the way of the CO2 utilization. And in this study, there are different way to produce methanol, like the CO2 hydrogenation. So one is the methanol production. Then you can also produce ethanol from CO2 hydrogenation. So CO2 hydrogenation means that you are mixing CO2 and hydrogen and in a reactor under the presence of some pressure and some temperature and catalyst, and you can produce various fuels like methanol, ethanol, dimethyl ether, formic acid, etc. Okay, and you can see the value added profit. Okay, so this is the profit, not the cost. So the profit will be about this much. So for methanol, if you can use CO2 and do CO2 hydrogenation, you can produce methanol and the profit will be 2.8 to 5.9 cents per kg. Okay. If you make DME, the profit is 69.6 cents per kg, right? If you make ethanol, that is 33.1 cents per kg. So therefore, it is quite possible to use this CO2 that you are capturing to form fuels and chemicals, and you can, and it is going to be economically viable, right? Because you are using renewable energy, renewable hydrogen, and you are capturing the CO2 and you are storing it, the energy in the chemical form, right? And then this methanol, this DME, ethanol, etc., can be used for any downstream applications for the production of power, etc. Right. So I will present a case study which is being done by one of my MS students currently. So here, this study is about the production of methanol. So methanol synthesis, and this is the equilibrium study where we have considered different methanation reactions. One is the CO2 plus 3H2 is going to CH3OH plus H2O. And here we have done the equilibrium analysis at different temperature and the pressure. And we can see that with the pressure, the CO2 conversion rises, right? With the pressure, CO2 conversion increases. And also, if we increase the temperature, the CO2 conversion decreases for this reaction, right? CO2 plus 3H2 going to CH3OH plus H2O. So for this reaction, the CO2 conversion decreases with temperature, but it increases with the pressure. Now when we are mixing CO2 and H2, there are many reactions going on. So this is one of them. And the next reaction is CO2 plus H2 is going to CO plus H2O. Okay, so this is another reaction. Now here you see again that the CO2 conversion increases with temperature, right? Here it is increases with temperature. Now, if you look at the third reaction, which is CO plus 2H2 is going to CH3OH, here you see that with pressure, the CO2 conversion, CO2 conversion increases. Okay, and with temperature, again it decreases. So it is possible to do this analysis of the equilibrium study, and based on that, we can arrive at the final reactor temperature. So in this case, the optimized reactor temperature is about 250 degrees centigrade. Okay, so that is what we obtained from the equilibrium study. And this is the schematic diagram of a methanol synthesis unit, which is producing 80 million ton of methanol annually. Okay, so what is done? We are basically using a mixing chamber where we are basically we are using the CO2 and hydrogen, and this is the hydrogenation reactor where we are mixing this CO2 and H2 and we are sending it through a fixed bed of catalyst. Okay, and after that the gases will come out and then it will go to the heat exchanger, and where it will reduce, it will get cooled, and at the same time it will heat up the incoming gases. Okay, and after 4, these gases will go to the heat exchanger 2. Okay, and then through heat exchanger 3 it is going to the flash vessel 1. Okay, and after flash vessel some of the gases will be condensed. Okay, and then it will come out to 0.9, and then you have to compress it to 10. Okay, and the remaining things will basically go to the throttling valve, and there again you have a flash vessel. Okay, and after that it will go to the compressor 2, and then again there is a mixing chamber. So this is a study that we are currently doing for generation of methanol. Okay, so after this after flash vessel 2, whatever gases are there, they have to be cooled down, and then they will come to the distillation unit, where you can basically separate out the methanol and water. Okay, so in this way we can produce methanol. And now we have done, after the equilibrium study of the reactor, so we have arrived the operating pressure and temperature of the reactor, and next we have to do the energy analysis and the exergy analysis. So here are the process parameters that we have decided. So H2 is to CO2 ratio is 3:1 that we have taken, right, by mole. Okay, so 3 mole of hydrogen is needed and 1 mole of CO2 is needed for this reaction, and the reactor pressure is 50 bar. Reactor temperature is 250 degrees centigrade. Flash vessel 1 pressure is 45 bar. Flash vessel 2 pressure is 0.5 bar. And then the preheating temperature of crude methanol is 85 degrees centigrade for the distillation. Conversion efficiency per pass is 20%. And the selectivity of methanol is 100%. Plant capacity is 80 metric ton, and then the million ton. And isentropic efficiency of the compressor is 80%. And the recycle ratio is 4.128. So these are the process parameters that we have taken, and then we have calculated we have done the energy analysis. Okay, so the input feed heating, that is at HE1, heat exchanger 1, it's about 8.5 megawatt. Okay, now crude methanol preheating, which is basically here, HE2. Okay, so this is 4.5 megawatt. Distillation unit reboiler, which is HE3 here, that is 4.8 megawatt. Energy released in reactor is 3.9. So this is the reactor, this is the energy released. Compressor 1 requires 0.4 megawatt, and compressor 2 requires 4.2 megawatt. And the pump work is 0.005 megawatt, that's 5 kilowatt, not much. Okay, so this is the result of the energy analysis. And here is also further results. So we are producing hydrogen, we are taking hydrogen, which is having a lower heating value of 120 megajoule per kg, and the flow rate of hydrogen is 0.48 kg per second here, right? The flow rate of methanol, that methanol you are generating, is 2.53 kg per second, that is the flow rate, and the lower heating value is 20.1 megajoule per kg. Now work done in the compressor 1 and 2 are this much, and the pump work is this much. So total work done is this much. So based on that, based on the calorific value or the lower heating value, one can find out the efficiency of the system, and the efficiency of the system is 81.75%. Right? How did you find it? You can multiply 0.48 into 120. So that is the input, and this much is also input. So you have to add this and this together. Okay, and what is the output? Output is 2.53 kg per second of methanol, and the LHP is this much. So you can calculate what is the energy available with the methanol, and then you take the ratio of that, and you will get the 81.75%. So that is the efficiency of the methanol synthesis. Comparison of system performance. Now one can basically do analysis based on one flash vessel and the two flash vessel. So in the diagram I have shown two flash vessels, and if you use only one flash vessel, then it causes a lot of penalty. Okay, so you can see, if you are using one flash vessel, then the hydrogen compression in megawatt is about 13 megawatt, and CO2 compression is 4.2 megawatt, and then the total work is, addition of these two, is about 17.1 megawatt. Now if you use two flash vessel like what we have done, it will reduce the compressor work significantly, because hydrogen compression cost decreases 0.4 megawatt, and then the CO2 compression cost is 4.2, total is 4.6. So therefore it is found that in two flash vessel system, hydrogen is separated at high pressure, and thus about 73% of work is saved in compression. Okay, two flash vessel system also reduces the system investment cost. So that is another point. Next, we have done the exergy analysis of different components, and I'm not going into much detail of this, but you can see the exergy destruction at different components, HE1, HE2, HE3, and the reactor, flash separator, throttling valve. All these components, we have done the exergy destruction calculations, and we have found out the efficiency, and we see that the lot of exergy is destructed in the heat exchangers, right? And the other systems are more or less good actually, right? So this is basically necessary to optimize the system. Based on this exergy destruction, you can basically find that where you are losing the maximum exergy, and then you can optimize the system based on your requirement. Now the equipment procurement cost is basically shown here. So compressor is 14%, reactor is 39%, and distillation unit is 27%, heat exchanger is 19%, pump etc. is about 1%. So EPC for the methanol synthesis unit is around $25.26 million. So various cost components of our total capital investment is calculated as percentage of EPC. Now here you can see that the TCI, total capital investment for this plant, is about 53% for the on-site cost, 10% is for the other cost, 23% indirect cost, and 40% outside cost. The plant consists of 3 units: MSCU, absorption plant, and the electrolyzer unit. Electricity for compressor electrolysis and plant electrolysis electrolyzer is based on some renewable sources. And then the total capital investment for the project is about $152.64 million. So based on that, we have estimated the cost basically, and the cost of methanol for the system that we have designed is about $353 per kiloliter, which roughly comes about 26 rupees per liter. And the market rate is this much. Okay. So yeah, so this is one of the analysis that we have done recently. It is yet to be published, and we have communicated a paper on this. Okay, so with this, I will come to the conclusion of my presentation, and thank you very much. And I'll be happy to answer any questions.
So dear participants, please unmute yourself and you can interact with Professor Shantanu sir. Any discussions?
Hello, sir. This is Dr. Ramesh from Bangalore.
Yeah, yeah.
What is? I was wondering this. What is the sweet gas?
Yeah, so sweet gas is basically, I mean, when you are basically having this CO2, etc., and then in that there will be a lot of impurities, and you have to remove them. Okay, and after removing that, you will be basically getting the CO2 for your purpose. Now, the sweet gas is basically one of the gases that you typically find from the post combustion capture. Okay, because there will be a lot of impurities in that.
You mean impurities are treated as sweet gas?
No, I mean basically it's a sour gas. When you are having the CO2, it is a sour gas.
Okay, okay.
Now you have to basically clean them and then make it suitable for this purpose.
But why it is called as a sweet instead of sour gas?
Really do not have any idea. I mean,
Okay,
yeah.
okay, okay. That's okay.
Yeah.
Thank you, thank you.
Yeah. Any other questions?
Any more questions from the participants? So you can also type in the chat box also. Any more questions?
Okay, I hope that I was audible, and then I mean, okay.
Yes, sir, you are audible.
Okay, no problem. Yeah.
Participants, any more queries?
I think that was a very theoretical kind of a thing there. Had we got something beyond that, would have been fine.
Yeah, towards the last, whatever I presented,
Yeah.
that work actually we are planning to make it in experimental setup.
Okay.
With this pandemic, the student was away, and then we could not do the experimental analysis. Although we synthesized some of the catalysts, etc. And
Okay.
then, but the reactor was we could not build on time, and
Oh.
therefore we decided to convert it onto the theoretical study. And
Okay.
the student is probably going to do this.
Sir, can you suggest any specific textbook or some kind of a literature for to understand the basics of this carbon capture system?
So here actually I talked about many things. I mean, and most of the items I gathered from the various reports and then the literature.
Okay.
Unfortunately, I'm not sure. There could be some of the edited books that is available from Springer.
Okay.
You can probably look at, but yeah, I do not have any such references.
Okay. Thank you.
Some of the review papers are available in various journals. Okay.
Okay.
Find it.
Any more questions from the participants?
So some of the chat box, there are some questions. CO2 capture from industries were updated in 2017. Not recent data is available. I mean, yeah, I do not have the recent data. So yeah. So there, I mean, to conclude, I mean, there could be many things that we should do. One thing is that we have to develop the better energies. I mean, the energy efficient systems. We can work towards the fuel cells on the hybridization of the systems. Then we can work towards the different CO2 capture technologies on the performance analysis of them. So these are the areas that we should focus collectively.
Any more participants?
So today, is there any other talk after this?
Sir, we are not getting any questions from the participants, so we are going to conclude.
Yeah.
So first of all, we thanks to Dr. Shantanu sir for accepting our invitation to give an expert talk on carbon capture, utilization and storage. So in the faculty development program on renewable energy intervention in industry, domestic and commercial applications. So thank you, sir. Our participants maybe gained a lot of knowledge from you. So even though you are not belongs to the renewable energy field, but you might be taught many subjects regarding the renewable energy. So in that, so you have given this topic a wonderful topic. So once again, thank you, sir. And I have sent an email to you, sir. So
Yeah.
you please go through that and our participants are asking PPTs. So if possible, you may send.
I will share this PPT with you.
Yes, you respond to that mail, sir.
Okay.
Thank you, sir, once again.
Thank you very much, and I hope that we'll have a better future. And good luck to everyone. And thank you for attending this talk.
Thank you,
Thank
sir.
you. Thank you. Thank you very much.
Sir, close our meeting, sir.
So this is the today's program. So with this, we'll end the session. So tomorrow we'll have the session by Dr. K. Srinivasa Reddy sir from IIT Madras. So sir is going to deliver a talk on solar energy technologies for industrial process heat and power generation. So all of you join at 11 a.m. tomorrow. So sir has given the schedule at 11 a.m. So all of you please join at 11 a.m. tomorrow. So thank you one and all for joining us today. Thank you all. So already feedback link is shared. So all of you fill it.
Sir, close cheyana, sir.
Feedback link వేసాను.